Okay, so let's look at graphing a base, and let's see if we remember our three main points. So in looking at any parent graph, 3 to the x, we have negative 1 something, 0 something, and 1 something. Okay, do you remember how it goes? So it's negative 1 comma 1/3, 0 comma 1, and 1 comma 3. And then there's an asymptote at x equals 0. So I can plot those points in. So negative 1, 1/3 right there, 0, 1, and 1, 3 right there. And sort of connect all of those like that. And again, there's this nice, lovely asymptote. I'll kind of use this highlighter here to do this. So that asymptote right there. Okay. All right, now let's use our transformation rules. So we come over here. What does that minus 5 do? Right? So it takes any ordered pair, and that's going to affect the x values because it's inside the function that we're subtracting. That actually means we're going to add 5 to any of our ordered pairs. Okay, so if I take, for example, the negative 1, 0, and the 1, I'm adding 5 to all of those numbers. So I should get, so negative 1 plus 5 is 4. So I should get 4, 0 plus 5 is 5, 1 plus 5 is 6, and the y values are the exact same numbers. So that's what I'm going to sketch real quick, and I'm going to do this in red so we kind of keep that straight. So I got 4 1/3, I got 5, 0, and I got 6, 3. So that's where our graph moves over to. Then let's do 3 to the x minus 4. Okay. So what's going on there? That minus 4 actually changes the y values. So we're going to subtract 4 from all of our y values. Alright, so going back to the original parent function here. Alright, so I want to keep the x's the same this time. So the negative 1, 0, and the 1. And this time I want to subtract all of the original. So 1/3 minus 4, 1 minus 4, 3 minus 4. Let's see, 1/3 minus 4 would be a negative 3 2/3. That would be 1 minus 4 is negative 3. And 3 minus 4 is negative 1. So I'll come over here and plot those. Alright, so negative 1, negative 2 2/3, so almost at 4. So 1, 2, right about there. Then we have 0, comma, negative 3, and then we have 1, comma, negative 1. Okay, so you kind of get a sense what's going on there. Alright, next one. Okay, what does that negative out front change? That actually, it's outside, so that's going to change the y's. Okay, so all of my x's stay the same, and the y's are now opposite. Okay, so come over here. We get negative 1, negative 1/3. And we have 0, 1. What was I thinking there? It's supposed to be 0, 1, not 0, 0. 0, negative 1, whoops. And then 1, negative 3. Okay, so you can kind of see that that's what that graph is doing. And then here we have, well, let's see, we got one more transformation. I'm running out of colors. I actually don't have purple. That's not good. Alright, so what's that going to do? So we're multiplying on the outside, so that's going to change all of the y's. So x's stay the same. Alright, so negative 1, 0, 1. And I want double the y value, so that'd be 2/3 2, and 6. Okay, so negative 1, 2/3, a little bit higher. 0, 2, and 1, 6 all the way up there. Kind of stretches up that way. Okay, so hopefully that helps. Now, if we our society's kind of changed a lot, and so we don't spend as much time looking at nature and noticing patterns and that sort of thing. But if we were the type of society that would look outside more, and we started keeping track of our own observational data and looking at different growths and decay rates, we would see this very interesting number that shows up. And this is what we refer to as the natural number. Referred meaning natural number, meaning out in the real world. If you look at seashells or you look at patterns of growth in populations, people having babies, that sort of thing, you typically find this constant that shows up in the way that the growth and the patterns are measured. So a lot of times in math, whenever we see this constant reminder of some sort of constant, we actually give it a fancy name. And so in this case, it's called E, natural number. Okay. E itself is named after a mathematician named Leonard Euler. That's right, it is pronounced Euler. And this is a number similar like unto pi. Pi deals with the ratio of circumference of perimeter to circumference to diameter in a circle. So pi we estimate using 3.14, but it actually keeps going on forever. E is sort of the same thing. We estimate that to be 2.71, even though it keeps going on forever and ever and ever. And so you can kind of see this very long decimal expansion of what E is. And a more mathematical definition of what E is, if we take, that's where this piece right here is, if we take 1 plus 1 over n and we raise it to the nth power, here's this a couple of examples, a couple iterations in that chart. The larger n gets, the closer and closer this thing gets to this 2.71 number. So as we get a very large n, we end up generating this E thing. Now, as far as this class is concerned, just know that E is 2.71. It is a number like unto pi, so it is considered to be an irrational number. It is actually a number and not a variable. So a lot of students sort of get that confused. It is a physical number, and we can do all sorts of the same things that we can do with other bases we can do with E. And so that's the last little topic that I want to address with this, is just sketching graphs of E and transformations of E. So let's fill in our 3 basic points in our asymptote. So negative 1, 0, and 1. We have 1 comma E, 0 comma 1, and negative 1 comma 1 over E. Okay, so start off with, let's see, E we said was about 2.71, right? So kind of close to 3. And again, 1 over 2.71 is kind of close to a third, but we've seen this pattern enough that hopefully we can generate what that means. Okay, and then we can take these same critical ordered pairs, this 1 over E, 1, and E, and we can actually do physical transformations and sketch pictures of these things. So, starting with the what does that minus 4 do? It's going to take all of our ordered pairs and it's going to change the x-coordinates. And what is it going to do to the x-coordinates? It's going to add 4 to it. Okay. So if we go back to our main ordered pairs, the y values stay the same. So we have 1 over E, 1, and E. The x values are the ones that are changing. So if we add 4, so negative 1 plus 4 gives me 3. 0 plus 4 gives me 4. 1 plus 4 gives me 5. So 3, 4, and 5. So I can come over my graph. 3, comma 1 over E, 4, comma 1, and 5e. We can shift those over. E to the x plus 3. So that's going to take all of my original ordered pairs, and that plus 3 is going to impact the y values. So I'm going to make them 3 times bigger, which means the x values are going to stay the same. And this is actually a little bit easier than it sounds. We're going to take 1 over e and add 3 to it, so that's 3 plus 1 over e. 1 plus 3 is 4, and e plus 3 is just e plus 3. I'm just going to estimate about, I know where 0, 4 is, and I know e plus, so e's kind of close to 3, so 3 plus 3 puts us a little bit closer to 6, not quite 6, and let's see, 3 plus 1 over e is like a 3 1/3, so I can still graph that even if I don't have exact locations, but I do know where 0, 4 is. That one's pretty easy to mess with. Then we got e to the negative x. Okay, so what does that do? That negative changes the x values. So going into the original parent graph, so we still have, see, instead of negative 1, it's 1 over e, 0, 1, that doesn't change, and then negative 1 comma e. And so we can kind of come over here and plot that. 1 over e is pretty close to the x-axis, 0, 1, and negative 1 e, so not quite 3. So we can see that that's what that graph does. And last but not least, what does the 3 do? So if I take all of my ordered pairs, 3 is on the outside, so that's going to change the y values. So I'm going to multiply those all by 3. So negative 1, 0, okay. So 1 over e times 3 is 3 over e. 1 times 3 is 3, and e times 3 is 3e. Okay, so again, we might not know exactly where those are, but we can estimate it. I know, for example, where 0, 3 is. And let's see, 3 over e, well, e itself is kind of close to 3. So 3, so this is, it's a little bit bigger than 1. It's a little bit bigger than 1, so I'm going to go negative 1, a little bit larger than 1. Let's see, 3e. 3e is kind of close to 9. So I'll put a little less than 9. And then I'll connect all those points just a little bit deeper. So hopefully that helps.